Hey everybody, Miss Knoll here. I am going to start Unit 6 notes, and Unit 6 is solving polynomials. So Unit 5 was graphing and operations with polynomials. Unit 6 is solving. And today's notes, I'm going to kind of lead off with what we did with quadratics. And we're going to solve polynomials by factoring. So we factored right before we went on this Corona break. So a lot of this will be review. So today we're going to focus on factoring quadratics like we did before, and then some special patterns. And we've also seen one special pattern before, and the new special patterns will work the same. So let's look what we've done so far. So previously, up to this point, you've already factored trinomials. Trinomials, if you know from the last test, is 3 terms. Ours were all quadratic. A problem like this, if you see my little bullseye, we would have used the slide method. We would have slid the 2 to the negative 20 and then factored from there. Perfect square trinomials, we would have factored like normal, meaning even though they call it some special way, we would have looked for 2 numbers that multiplied to 16 and added to 8, and that would have been 4 and 4, so we would have factored as x plus 4, which conveniently is also x plus 4 squared. This was also a special pattern. I just didn't preach its necessity because you could do it without the pattern. And then we had a difference of squares pattern. That pattern we did use. And I did kind of preach that if you had a perfect square minus a perfect square, that would always factor into whatever squared first. So a was being squared first plus what was being squared second. And then the same thing with the minus. So this is something we did before. And then the last way we factored before was a GCF. So here 8x squared plus 20x, the GCF, or greatest common factor, is 4x. So that 4x was undistributed. So these are all ways we factored it before, and we're going to start off just reviewing there. And then we'll move into special patterns for polynomials. All right, so to be factored completely, so remember, polynomials, poly means many, many terms. Quadratics typically had 2 or 3 terms. So these polynomials could have many terms, but to be factored completely, it has to be a product of unfactorable polynomials, meaning those sets of parentheses next to each other that can't be factored any further. Let me just give you a numeric example before I go to the polynomial one. Like 6 we know is a number, but to be factored completely, that's really 1 times 2 times 3. Right? I change into these, and I'll even put parentheses, because times I can put with parentheses. So to be factored completely, you have to list all factors that can't be factored any further. So examples we've seen to be factored completely is if you see numbers or sets of parentheses where you can't factor any further. And this is really review. So as I go through these examples, we're going to factor it just like we always did, meaning first, we'll look for a GCF, and then second, if we can, we'll unfoil it. And this is really, we did a lot of factoring before we went on this long break. So if I look at example A and I look, well, is there a GCF? Yes, there is. Each of these terms has a factor of x. That means the GCF is x, so I can pull an x out. So if I take an x from x cubed, that's going to leave me with x squared. If I take an x from 2x squared, that's going to leave me with 2x. If I take an x from the minus 15x, that's just going to leave you with minus 15. So that was step 1. So check. We did step 1. There was a GCF. Now second, let's see, does this unfoil? Or for us, are there 2 numbers that multiply to negative 15 and add to positive 2? Yes, there are. So those 2 numbers Sorry, I'm writing with my fingers. That's why the handwriting is a little bit sloppy. My resources aren't the best here at home. So the two numbers that multiply to negative 15 and add to 2 are positive 5 and negative 3. And now if you look at these expressions, I mean, I can't factor x minus 3 any further, I can't factor x plus 5 any further, and I can't factor x any further. So that's my final completely factored answer. Let's look at example B. So again, I look for a GCF first. This one does have a GCF, a 2, right? You can get a 2 from 2y to the 5th and 18y cubed. And you can also get a y cubed from both of these terms. So the GCF here is 2y cubed. And if I divide it, or if I take away a 2y cubed from 2y to the 5th, that's going to leave me with y squared. And if I take a 2y cubed from 18y cubed, that's going to leave me with a minus 9. So again, I found the GCF first. And now does this unfoil? And yes, it does. Notice y is being squared and 9 is 3 squared. So if I scroll back up here real quick, here's that difference of squares pattern. I have y squared minus 9 squared. So that's going to factor, this a would be y, right? Y squared. So this would be a y and this a would be a y. And then 9 is 3 squared, so both of these b's would be 3's. Again, this is review. We did this a lot before break. So my final factored completely answer is 2y cubed. And this y squared minus 9 will factor as y plus 3 and y minus 3. And again, it's fully factored because nothing can be factored any further. Last example, I got 4z to the 4th. Or let me just start with my GCF. Is there a GCF? Obviously, there's a 4. And then if I look at my z's, I can get a z squared from each of these terms. So my GCF is 4z squared. And then that's going to leave me with z squared. Because if you think about it, 4z to the 4th, I'm dividing out, I'm undistributing a 4z squared. So it's going to leave me with a z squared. 16z cubed will now become minus 4z. And the plus 16z squared will be plus 4. And now again, I look, well, can I unfoil this? Are there two numbers that multiply to 4 and add to negative 4? Yes, there are, you betcha. Those two numbers are negative 2 and negative 2. So this would be z minus 2 times z minus 2. Whoops. And then some sources, this is called a perfect square trinomial. You could, I'd accept that answer right here. But you could, because z minus 2 is being multiplied by itself, you could write it as z minus 2 squared. So page 1 of the notes, that was all review. I mean, we factored like that a lot before we went on this break. What's new, kind of new, are factoring patterns. So for polynomials, we have two factoring patterns. One we've used before was a difference of two squares. Let me highlight it instead of underline it. So we've used the difference of two squares pattern. I wrote it on the previous slide. I'll write it again. That was if you had a perfect square minus a perfect square, it would always factor into whatever was being squared first plus what was being squared second, and then whatever was being squared first minus what was being squared second. And before I move into the new patterns, I'm going to give you a few better examples of that. All right, so let's look at a few examples of this pattern, a squared minus b squared And that's going to always factor to a plus ba minus b. I'm going to try to go to kind of advanced example first. So let's think about this quadratic, 4x squared minus 81. So way back when we did this in class, I'd say, well, if you see two terms and you see some squares, you should be thinking about using this pattern. Well, here I see two terms with a minus, and I see a little square. So I asked myself, well, I see x is squared, but what squared gives you 4x squared? And you all, I know you all would tell me, that's 2x, right? 2x times 2x, that gives you 4x squared. And well, what squared is 81? You all would say that's 9 squared. So using this pattern, obviously you kind of see that a matches the 2x. So in my pattern where that a is, we're going to put a 2x. You also see b, that matches 9 now because I see something squared. That means these b's are going to be 9. So this quadratic would have factored to 2x plus 9 times 2x minus 9. And we did that pattern at the very end of first semester. And the ones you learned today are going to be very similar. So let me go back to today's patterns. So here are today's patterns. There are sum of cubes and a difference of cubes. So if you need to pause the video to write those down. I mean, obviously now that we're at home, you don't really have to memorize these. I'd usually make you memorize them. So write them down somewhere convenient. But they work the same way, meaning if I have something cubed plus something cubed, it will always factor this way. And then same idea with the minus. I'll give you a list of cubes, or you could generate your own, but some common cubes are 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, and so on. I mean, you could generate more. Those are typically the ones we see. So if I look at this first example, I see a plus, I see an x cubed, so I'm thinking, well, I hope 64 is a cube, and yep, there it is in our list. So this pattern's going to work. So what's being cubed first is x, and then we now see that 64 is 4 cubed. So that means a is x and b is 4. So when I go to use this pattern, I'm going to kind of fill in the blanks. Instead of a plus b, we're going to use our a and b, and same thing with the rest of the pattern. So where a is in the pattern, I'm going to use x. Where b is in the pattern, I'm going to use 4. So if you look at, there's my a's, a. My b's are here. So let's see what we got. So a plus b, we're going to have x plus 4. And then a squared, we're going to have x squared. A times b, that's x times 4 is 4x. And then b squared, 4 squared is 16. And that's it. I mean, that's as tough as it gets. Even in b, I don't see cubes, but remember, factoring, we look for a GCF first. So the GCF here is, it looks like it's a 2z squared. And if I undistribute a 2z squared, I'm going to be left with 8z cubed. Well, 8 was in the list I wrote up here. That's definitely a cube. And 250 divided by 2 is 125. So it's going to fit this difference of squares pattern. And I think about, well, what cubed is 8z cubed? Well, that's 2z cubed. And then 5 cubed is 125. So in the pattern, a minus b is going to be 2z minus 5. And then a squared, 2z squared is going to be 4z squared, because it's 2z times 2z, plus 2z times 5 is 10z. And then minus b squared, or sorry, plus b squared, 5 squared is 25.